Welcome to another lecture on design and analysis of algorithms. We will see one more problem which can be solved nicely using dynamic programming today. The problem we are going to solve is scheduling with startup and holding costs. Okay. Let me define this problem for you. Okay. So, in this problem we are given a machine which has the capacity of producing 1 unit of something, whatever it is, per day. However, if I want to start a machine on some day, which is, so what I mean by that is that if the machine was not on yesterday and I want to get it working today, then I have to pay a startup cost. And that startup cost is some S units, which is defined as a part of the input. Clarifying again, if the machine was on yesterday, then I don't pay a startup cost today if I want to keep the machine working. If the machine was off yesterday, but I want to start it today, then I will have to pay a startup cost. We also have a warehouse to hold units which have been produced. So, if I produce something today and it is not to be delivered today itself, then it goes into a warehouse. But of course, if I place something in the warehouse, I have to pay some rent. So, let us say that we will call this the holding cost, and that holding cost will be some H rupees per night. The main input to the problem consists of a daily demand for n days. So, we are given a vector d of 1 through n, in which d of I represents the demand for the ith day. We are also given the startup cost S, the value of S, and the value of H, the holding cost. And what we are supposed to produce is a schedule. So, we are supposed to produce a vector p of 1 through n, in which p of I denotes whether or not the machine is to be kept on the ith day, or in other words, whether the machine should be producing anything on the ith day. So, the final requirement, which might be obvious perhaps, but let me state it nevertheless, is that at the end of n days, all the units that have been manufactured must have been delivered. So, we cannot be left with any inventory at the end of n days. Okay. And of course, it is possible that the demand that has been given to us is just not satisfiable, because after all our machine can only produce 1 unit per day. So, in n days the machine can produce n units. So, certainly if the total demand is more than n, we will not be able to meet it. There may be other conditions as well under which the demand could not be met. But whatever these conditions are, our algorithm must report if the given demand cannot be met. So, let me now take an example to illustrate this problem better. So, in this example, this is the demand vector that is given to us. So, what this means is that on day 1, nothing needs to be delivered. Day 2, nothing needs to be delivered. On day 3, there is an order of 2 units which has to be delivered. Day 4, day 5, day 6, nothing has to be delivered. And on day 7, there is an order of 3 units. The holding cost, that is the cost of storing 1 unit in our warehouse, is 1. So, it is 1 per unit, and the startup cost is 5. So, here is one possible schedule or one possible production plan which will meet this demand. So, I have shown this in a tabular form over here. So, we have days on the x axis. So, 1 through 7, since there are 7 days, the demand is given to us for 7 days. On the 3rd day, there is a demand of 2 as specified over here, and on the 7th day also there is a demand, and in this case the demand is of 3. Here is a production plan which will meet this demand. So, notice that on this day 2 units have to be delivered, and on any day we can only deliver 1 unit. So, which means we have to start producing earlier. So, say in this case we start producing on day 2. So, we will produce on these 2 days, and then to meet this demand we will produce on these 3 days. So, the machine will be idle on this day and on this day. Since the machine is going to start having been idle on the previous day, there will be a startup cost on day 2. So, this will be a cost of 5. Similarly, on this day the machine will have to start again having been idle on this day. So there will be another startup cost. On this day, day 2, whatever has been produced is not going to be delivered. It is only going to be delivered the next day. So it will have to be held in our warehouse, and so there will be an inventory cost of 1. Similarly, on this day, whatever is being produced will have to be held in the warehouse. Whatever is being produced in the warehouse on this day will also be held. So at this point, there will be 2 units in the warehouse. Okay, so a holding cost of 2 will be encountered over here. This is of course not the only possible plan. Here is another. So in this case, what we have done is, instead of keeping a gap on day 4, we have begun the production earlier. But notice, if we begin the production earlier, then we have our holding cost earlier as well. So in fact, on the 4th day itself, we have to hold in our warehouse whatever unit has been produced. On the 5th day, whatever has been produced has also to be held in addition to whatever was produced yesterday, the day before that. And finally, whatever is produced on the 6th day will also have to be held, and all these 3 units will have to be delivered on the 7th day. Which of these is better? Well, let's calculate the times taken, the cost of each. The cost of the first plan, that is this one, is simply the startup cost, which is 5 plus 5 here, plus 1 plus 1 plus 2. So this cost for this first plan is 14. The cost for this plan is 5 startups, 5 for the startup, and then 1 plus 1 plus 2 plus 3, which is what I have written over here. And this adds up to 12. So clearly, this plan is better. Our question in general is going to be to consider all such possible plans and figure out which is the best one. So this naturally suggests a brute force algorithm. So we will generate all possible plans. For each, we'll evaluate the costs, and then we'll pick the best. Unfortunately, the number of such schedules or such plans is going to be exponential in n, where n is the number of days. So this is going to be just too slow, and we would like to have a faster algorithm. This is where dynamic programming comes in. So here is a quick overview of dynamic programming. Okay. So the first idea is to find some kind of a recursive solution. How do we do that? Well, we cast our problem as a search for some object over a certain search space. So it's useful to define the search space quite clearly, as well as it is important to define clearly an objective function which is to be minimized, or sometimes it has to be maximized. Whatever it is, it has to be defined very clearly. Then we design an algorithm which searches this space. Typically, the algorithm is going to partition the search space. So it's going to say, let's divide the search space into pieces, and each space, each part of the space or each subspace is going to be searched separately. So I search the first subspace and I get the best solution or the optimal solution in it. What I mean by that is the solution which minimizes the objective function, or if we want maximization, the solution which maximizes that objective function. So we calculate the best or the optimal in each search space and then return the best of the best. So that is the general idea of getting a recursive solution. Dynamic programming, however, doesn't stop at this point. It proceeds further in the following sense. The idea is that we will characterize what the recursive calls are in this part. So essentially, we are going to ask the question, what is it that what are the problems that we are solving? So we essentially make a table of all those problems. And in each cell of the table, we would like to store the results of those. So we will define such a table, then we'll define a procedure for filling table entries, and this procedure will be a direct procedure. So it won't be recursive in particular, and it will assume that if I want to fill a certain table entry, I can use entries which have been filled earlier. So this will fill entries in the table given that other entries have already been filled. So in this recursive procedure, the recursive procedure might be slower because it might calculate the same quantity several times, whereas in this case, when we make the table, we will carefully think about what it is that needs to be calculated, and we'll calculate that exactly once. So that's going to give us our efficiency. So what we would like to do now is to apply this whole idea to our given problem. The first step in this is to find a recursive solution. So we want to cast our problem as a problem in the recursive fashion, our algorithm in the recursive fashion. So here is how we might think of a recursive algorithm for our problem. So we would like to solve an n-day problem. So typical steps in it might be that we somehow solve the first day, and then we recurse on the remaining n-1 days. Now, unfortunately, recursing on n-1 days will depend upon what happens on the first day. So say, for example, if the machine has been switched on the first day, then when I recurse, this information is very useful to me. So if the machine is on, then in the first day of the recursion, I don't have to pay the startup cost. So which means our recursion must somehow include additional history information. The most natural way of doing this is to generalize our problem. So let's see that. So our generalized scheduling problem looks something like this. It has the same inputs as before, except there are some more. So it has inputs the demand as inputs the demands for the n days, the startup cost, the holding cost. And then there are two additional inputs, an input I, which gives the initial inventory. What I mean by inventory is how many units are already in stock on day one. Okay, so when I begin the whole thing, it is possible that I already have some units in stock. So that number is specified as a part of the input, and that is this number I. Then on the day on which I begin, the machine might already be on or off, and that is specified by this variable m. So m can take values on or off, I can take values in any integer. The rest is similar. Well, I should point out that our old problem, which we had defined earlier, corresponds to having I equal to 0, that is, there is no inventory when we start, and m equal to off. So this is a generalization in the sense that now we allow I and m to take on a wider range of values. Our output is as before. We are supposed to produce a production schedule, and the requirements are the same, that at the end of n days, everything that has been produced must be consumed. So let us now try to design a recursive algorithm for this problem. So the first step was to design or to think about a search space for this problem and the objective function. So let me call S the search space. So what is the search space for the input problem as given? Well, the search space will contain all possible schedules for this instance, and the instance is characterized by these inputs. So an instance is defined as D, S, H, I, M, where D is a vector of n elements. If it helps us to think about, we'll think of each schedule as being an n-bit vector. So each bit specifies whether the machine is to be on or off on the corresponding day. The objective function is a cost, and it just consists of the sum of the holding and the startup costs. And our goal is to get the minimum cost schedule from this space S. Next comes how we are going to partition this. Here is a natural way in which the space can be partitioned. So we'll ask, what happens on the first day? So in subspace S sub p, we will put all schedules in which machine is producing on day 1. In subspace S sub I, we will put all schedules in which machine is idle on day 1. Now this union this is this, in the sense that in every schedule, in every element of S, Either the machine is producing on the first day or it is idle on the first day, and therefore this is equal to this union this. So we have a partitioned S. And so the next question is, how do you search each of these subspaces? So let us look at S sub p first, and we will try to think of how to search S sub p. Here is the key idea in devising recursive algorithms for optimization problems. So if P is a least cost element of S sub P, okay, then the question we should be asking is, will parts of P themselves be least cost solutions to some smaller instance? If they are, then we can use recursion. So this is the so-called optimal substructure idea. So P is, if P is an optimal solution in this subspace S sub P, the question is, will parts of it be also optimal for a smaller subproblem? And in fact, it turns out in our case that that is true. So let P 1 through n be a least cost schedule in S sub P. We'll show that parts of it will have to be optimal for a subproblem, for a smaller instance. Okay. So if P is a least cost schedule, what do we know about it? Well, we know that P of 1 is equal to true. Why? Because P is a least cost schedule in S sub P, and S sub P is a set of schedules in which the machine is on the first day. So P of 1 must be true. P of 2n is the rest of the schedule, but now I can think of P of 2n as a schedule for the residual instance from day 2. Okay. So let me clarify this. So our original instance was this DSHIM with D n an n integer vector. Okay. The residual instance is just a part of this which begins on the second day. So in the residual instance, we have only demands for days 2 through n. Then S is the same, the startup cost doesn't change, the holding cost doesn't change. Okay. However, the inventory on day 1 is going to be different, on day 2 is going to be different. On day 1, the inventory is 1, okay, and on the first day we produced. Okay. So of the inventory that was present on day 1, okay, we are going to deliver D of 1, okay, which was what the problem requires us to deliver, and then to it will add whatever we produced on day 1. So this is the inventory for this instance beginning on the second day. The final component is the machine status. So over here the machine status could have been whatever. Okay. Now we know that since we did produce on the first day, the machine status had better be true. So this is the residual instance, and clearly P to n must be a schedule which satisfies this residual instance. Here is the key lemma. This lemma says that not only does it satisfy this residual instance, but in fact it has to be an optimal schedule for this instance. Okay? Or in other words, it has to be a least cost schedule for this instance. The argument for this is actually fairly straightforward, and it's sort of the typical argument in dynamic programming, like arguments. Okay. So we'll do the argument by contradiction. So we'll assume that P to n is not an optimal schedule, which means there had better be a schedule Q to n which is optimal for this instance, and its cost had better be smaller than the cost of P to n. So cost of Q to n must be smaller than the cost of P to n. But now let's consider this schedule R, where R follows P on the first day, or in other words, R is true on the first day, okay, and on the remaining days it follows Q. Okay. Clearly, this is a valid solution for the original instance. Why? Because, well, on the first day we produced, and then we were left with this instance, and that's what Q took care of. Now, what is the cost of R? clearly cost of r must be smaller than the cost of p. Why? Because cost of r is nothing but the cost for the remaining days plus the cost of p, the cost of the first day. Okay. This is the cost of r. Cost of p is the cost for the first day plus cost for the remaining days, which is not q2 through n, but p2 through n. But in p, we are adding this, whereas in r, we are adding this, and this is smaller than this, and therefore cost of r must be smaller than cost of p. But remember, we assumed that p is a least cost schedule in S sub p. But here we are showing that there exists a schedule r which has even less cost than p. Okay. And also the first element of r is true because it is p1 itself. So r also belongs to S sub p, and therefore we have a contradiction, and therefore our basic assumption must have been false, or in other words, our lemma must have been true, that p to n is also optimal for the residual instance. So this tells us how to search the space S sub p. A similar idea works for the space S sub I. So let's say I 1 through n be a least cost schedule in S sub I. Then I 2 through n is a least cost schedule or is optimal for the instance d2n s h I minus d1 false, or this is the residual instance. So see that the last component, the machine status, is false because Si consists of schedules in which the machine is off on day 1, therefore this is false, and the original inventory was I, but on day 1 we delivered something without producing, so the new inventory is I minus T1. So this is the residual instance, and this lemma claims that I2 through n must be optimal for this residual instance. So we have accomplished the goals that we set. So we have shown how to search S sub p and how to search S sub I, and this has been done by using recursion. So we are essentially ready to build a recursive algorithm for solving this problem. Here is an outline. So we'll call our algorithm opt schedule. So it will take as arguments the entire demand, and when I write d1 through n over here, I simply mean that d is going to be a vector with n elements. It will take additional argument, which is the startup cost, a holding cost, the inventory at the beginning, and the machine status at the beginning. There will have to be some base case that will have to take care of, but this is sort of the core of the recursive algorithm. So in this part, we are going to search the space S sub p. So we are going to find the optimal schedule for the residual problem, okay, assuming that on the first day we do produce, okay, and that will be our schedule p1 through n. I1 through n will likewise be the optimal schedule for S sub I, and in this case on the first day we are not going to produce anything, and this is just the residual problem given that we don't produce anything on the first day. So these are the problems which we exactly looked at in the two lemmas that we just saw. And then we are going to look at the cost of the first schedule, the cost of the second schedule, and we are just going to return the best of these. So this is the best of best idea. Okay, so this is the best solution in the first subspace, this is the best solution in the second subspace, and what we are returning is the best of the bests. A number of details have to be filled up over here. Okay. However, you should be able to argue that this algorithm will take time O of 2 to the n. Okay. So just write a recurrence and this will just come out. Okay. Okay. So what we are going to do now is not fill up the details, the remaining details, and there are a few important details which are actually missing over here. But what we have done is we have essentially identified what kind of recursion we are going to have. So we'll just proceed to the next step of our agenda. Okay, so the next step in the dynamic programming idea. So this step is the key step of dynamic programming, which is characterizing the recursive calls. So the first observation is that opt schedule is always called using arguments dj through n and shim, okay, where j can be any number. Okay. So let me just observe. Let me just point out why this is. So initially, opt schedule is going to be called with the entire input, okay, but then later on it is going to be called with the residual problem, in which we are only going to pass the subarray beginning with the second index. Now what happens in this call itself? In this call, we are going to again throw out the first element of the demand array, and then we are going to call it with the rest of it. So when we do the recursion on this, we will be calling it with d3n, and then when we recurse on that, we will be calling it with d4n and so on. So in other words, the arguments are always going to be of this form, that we will be that the first argument that is going to be passed will be some subrange. Okay. Well, it will always be a terminal subrange of our input d. Okay. So a suffix of that d array, okay. And then these could be pretty much anything. Okay. So j has to be some number between 1 and n. So the largest index is n, and j could be anything until then. S and h, note that S and h just get passed without any change whatsoever. Okay. The inventory can be at most n. Why is that? Well, we have n days during which the machine produces 1 unit per day, and therefore the inventory cannot ever build up to more than n. So this argument will be an integer at most n, and the last argument could either be true or false. So we have a reasonably good characterization of all the recursive calls that could get made in our recursive algorithm. Okay. So the characterization says that these are the arguments which are going to be passed, and each argument can vary in this manner or not vary at all. The next step of dynamic programming says, well, now that you have identified what the recursive calls are going to be, make a table in which we are going to store the results. Okay. So we'll construct a table T, in which T will have 3 indices, j, I, and m. So T of j, I, m will store the result of opt schedule of dj through n, s, h, I, m. Okay. Okay. The point of making the table really is that we just want to focus, we just want to make a list of what are the sub-problems that we are ever going to solve. So this is what we will do. Now we can work with this table T. However, dealing with schedules is a little bit cumbersome. Okay, so we are going to simplify the problem just for a few minutes. So instead of working with entire schedules, we'll just work with the cost of the optimal schedule. Okay, so in the table T, we were planning to store in each cell the entire optimal schedule. Instead of that, we will build a different table, let's call it C for cost. It will have very similar entries, okay, similar number of entries with similar indices, and in this we'll just store the cost of the optimal schedule. Okay. Okay. So we are now going to work with this table, and what dynamic programming requires us to do is to figure out how entries in this table depend upon each other. So in other words, if the entry CJIM has to be filled, assuming the remaining entries are full, what is the exact computation that needs to be done? So we need to devise some kind of a recurrence for CJIM. Let me just remind you that CJIM is the cost of this optimal schedule for the sub-problem, or for the residual problem actually, djn shim. Okay. Let me just remind you that we didn't have sh in the table because they are fixed throughout the execution anyway. Here is what the optimal schedule for djn is going to look like. Okay. So I claim that the optimal schedule for djn shim is going to be the schedule with the lower cost from this schedule and this schedule. This really comes from the procedure that we wrote a minute ago. So let's just see that. So let me just write this down. Okay. So my claim is, or what I want to examine is the optimal schedule for d of j through n, okay, s h I m. This is what I want to understand, and I want to figure out how, what will the optimal schedule to this be. Okay. So let us go back to the code that we wrote, okay, or the recursive algorithm that we wrote, and we said that the optimal schedule for d1 through n shim is going to be one of these two. Okay. Now, one of these two, when d is passed as the entire array, is this, but when only a range, a smaller range is passed, so the first argument is 1, what will this be? So the first schedule will simply be true concatenated with opt schedule, okay. And this time, instead of passing 2 through n, I should really pass j plus 1 through n, because this was just dropping the first element. So if I drop the first element from this, this will become d of j plus 1 through n s h I m. Okay. What about this? So this will become false and opt shed. Okay. Okay. D of j plus 1 through n s h, and in the inventory I should really remove what was produced on day 1. So, or not on day 1, but on day j, and I should have m. Okay, so this is what I should have. Here, instead of inventory being I should really have I minus d of j plus 1, because since the machine was on the first day, I have to have a plus 1 over here. Okay. So you can see that this is exactly what I have written over here. So true concatenated with optimal schedule for j plus, the demands j plus 1 through n, s h I minus dj plus 1 and true, and the other schedule, which is false optimal schedule of false concatenated with optimal schedule of d j plus 1 through n, s h I minus dj and false. So now we understand what optimal schedule itself is. So we just have to now figure out what the cost, the relationship amongst the costs is going to be. So CJIM is simply the cost of this. Okay. So what is that going to be? Well, this is the least cost of this. So CJIM had better be the minimum cost of the cost of these two schedules. Okay. So what is the cost of these two schedules? Well, the first schedule starts with keeping the machine on day 1. So here there is some potential for incurring a startup cost. Whether the startup cost is incurred depends upon whether this m was on or off, or true or false to begin with. So if m is true, then there is no startup cost, or the startup cost is 0. Okay. If m is false, then the startup cost is s. So this expression which I have written down over here is to be understood as, it's to be understood as the C expression. Okay, so there is a C expression, question mark, true value, colon, false value. So if m is true, then this bracket evaluates to 0, otherwise it evaluates to false. In other words, this bracket over here represents the startup cost. It's either 0 or s depending upon m. Then on day 1, there is going to be some inventory cost. So this inventory cost is given over here. So the inventory for day 1 is going to be this. Whatever the old inventory, subtract whatever was delivered on day j, add whatever was produced. So times h will be the inventory cost, and then there is the residual cost. So it's just the cost of this part of the schedule. But this part of the schedule, the cost of this is simply Cj plus 1 I minus dj plus 1 true. Okay, so we have related the jimth entry to the j plus 1 I minus dj plus 1 true entry. Okay. So we have to take the minimum of this quantity and this quantity. So in this case, the computation of the cost is actually simple, because there is, since the machine is off on the first day, this is false, there is no startup cost, but there is some holding cost. So what is the holding cost? On day j, something gets delivered, so the inventory gets reduced by I minus dj. So the inventory is just this, and the inventory cost is just this, and this is the cost of the residual problem. So now we have a recurrence connecting Cjim to other entries in the table. So this is the one other entry, and this is one other entry. There are some problems though. Okay. So when we wrote down these numbers, we haven't so far considered the possibility that I minus dj plus 1 or I minus dj might become negative. That doesn't make sense. So I minus dj plus 1 or I minus dj is the inventory. So it doesn't make sense for the inventory to become negative. So we somehow have to take care of that. Okay. Essentially what is going to happen is, what should happen is that we should check if we want to consider this schedule, okay, and if we are requiring that I minus dj plus 1 be negative, then we should really not be considering it at all, and we should just use this. Okay. Here is a very nice fix to this, a simple fix. So we are going to define C of jim to be infinity if I is less than 0. So let's see what this does. So in this example, for say in this alternative, for example, okay, if in this table entry, this is some negative number. So we are asking for C of j plus 1 some negative number true. Now this entry would be defined as infinity, which would mean that this number would be infinite. But if this number is infinite, then this entire cost would be infinite. But since we are taking the min over here, that would force us to look at this cost. So essentially we would be ignoring this cost. Okay. So by defining Cjim equal to infinity, we are saving ourselves the trouble of checking whether the indices are less than 0, okay, in this expression, and automatically getting the same effect. Okay. Now of course you might ask, if we want to do this for all I less than 0, do we need to consider all the infinite negative numbers for I? Well, we don't, and there is a simple reason for it. Remember that the demand on any day cannot be bigger than n. Why? Well, if the demand is bigger than n, then we cannot fulfill that instance anyway, and so we can check at the beginning whether the demand on any day is bigger than n, in which case we just reject, we just say that this problem is unsolvable. So this algorithm, or whatever algorithm we are going to design, will only be called if d of j is less than or equal to n. But if d of j is less than or equal to n, then we are only subtracting n from whatever has to be a positive number earlier. So in which case it suffices if I is bigger than or equal to minus n. So we only need to consider only a few negative values of n, that is values of I, that is values going from minus 1 to minus n. So in other words, our table is not going to become too large. The final problem that we need to consider is the base case. So we related entries in the table with other entries, but this cannot go on forever. So some entries we have to set ourselves. So these are the entries for the last day schedule. Okay. So remember that C, J, I, M were the indices for the table entries. If you look at the last day, then the first index over here should be N. So in this case, we are asking for a single day schedule. So we should be able to set this without much ado. So here is the idea. If we want to figure out what C, N, I, M ought to be, and we need to figure whether there is a legal schedule. So the main condition over here is that whatever inventory we come in with should not be too large or should not be too small. If it is too large, then even after satisfying the demand, we will be left with inventory. And that is illegal. So that will not constitute a valid schedule. If it is too little, we may not be able to satisfy D of N at all. So the inventory should be just enough to satisfy the last day's demand. So very simply, if I is the last day's demand, if I takes the value last day's demand, then we should run with the machine off. We should not produce any more units. And so in that case, the cost for the last day is simply 0. So C of NIM must be 0 if I is equal to D of N. If on the other hand, the inventory is just one less as we come into the nth day than what the demand is, then well, we had better produce to make up the inventory that we want, to be able to deliver whatever is needed to be delivered. So we will have the machine be on, and now for the last day, we need to run the machine. Okay. So our cost is going to be 0 if the machine was already off, was already on, and S if the machine was off. So this is again the similar C-style expression which evaluates to either 0 or S. For all other values of I other than Dn and Dn minus 1, this means that we have either too much inventory or too little inventory, in which case we should set the cost to be infinite. So that takes care of the base case as well. So let me pictorially show what has happened over here, okay. Or let me pictorially show what our table is going to look like. So our table is going to look like something like this. So on this axis, I am going to have the days. Okay. On this axis, or this is where how J is going to vary. On this axis, I am going to have inventory. Okay. So this is inventory greater than 0. On this side, I have I less than 0. And on this axis, okay, into the page, if you will, I will have M. Okay, so this corresponds to say on, and this corresponds to off. Okay, so I will draw the off in a different color. So it will look something like this. So there will sort of be these two sheets. Okay, so even the second sheet okay, so our table is going to look something like this. Now, how did we fill the table? Well, so in this case, we looked at the last column on the days side. So this is what we filled out. Okay, well, right. So this part we filled out. So this is nth day. And this in this second part, in the off side also we filled it out. Okay, so these values are known. Okay. Then because of this, we defined Cjim equal to infinity wherever I was 0. We have also filled this out. So this part. Okay. So these parts are filled out to begin with, okay, by very simple ideas. So the recursion part only comes for this part and this part over here. So how is that filled? Well, that is filled using these expressions. So essentially, if I want to fill this entry, what am I going to use? Well, I am going to use some entry in the j plus 1th column. So I'll use some entry from this column, okay, and also the corresponding column of the off side of the machine being off, because so I'm getting Cj plus 1 and true and Cj plus 1 and false as well. Okay, so this entry depends upon the next column. So now our calculation is actually quite straightforward. Okay, so this part has already been filled up very easily by the last day's calculation and by this calculation, and then to fill each entry we will use just this expression, and this entry can be filled in constant time, as I have seen over here, as I have shown over here. So basically the idea is that we fill the entire table in decreasing order of j. So we start from here and go backwards and we fill in the table. Okay. So the number of entries over here, well, let us just calculate that carefully. J ranges from 1 to n. Okay, so here it is 1 and here it is n. Okay. I goes from minus n and it goes all the way to plus n. Okay, so there are 2n plus values for I, and m can be on or off. So there are only 2 values for m. So the total number of entries in the table is just all possible choices for j, all possible choices for I, and all possible choices for m. So n times 2n plus 1 times 2, or O of n squared. Time to fill each entry. Our recurrence can be evaluated in constant time, or each single step can be evaluated in constant time. So it is O of 1, and as a result, the total time is O of n squared. So we will fill the entire table in O of n squared time. Okay. We should ask, well, we have filled this table, but which part is the one that we want? Okay. So coming back to this is the entry which we want. So at the end of it, this is our final answer. Or, I'm sorry, not this, it is this. Okay, this is the final answer, or the optimal cost is found in entry 1, 0 false of the table. Okay. So 1 is the j value, 0 is the I value, so it's this entry on this axis itself, okay, and it is in the off or the false side. Okay. So this just says what is the cost of generating a schedule for the entire demand, given that there is no inventory to begin with and that the machine is off. The final topic is, how do I find the schedule given the table? So remember that C1 off was the cost of the optimal schedule. Now this cost is going to be a minimum of some costs. Which costs? Well, we noted that if I want to calculate this cost, it is the minimum of some cost in this and some cost in the corresponding column over here. So C1 off would be the minimum of some expression involving some column, some element in the next column on the off side, as well as some element in the next column on the on side. Okay. So we simply check whether C1 is equal to the first term or the second term. It is the minimum, so it should be equal to at least one of these. If C1 off is equal to the first term, what do we know? Well, we know then that this must be generated by using the first term or by keeping the machine on during day 1. If this term is equal to the second term over here, then the machine should be off on that first day. So in this case, in this way, by knowing the optimal cost, we were able to, and knowing the table, we were able to figure out whether the machine should be on or off on the first day. And we were also able to figure out what the corresponding entry for the optimal schedule for the residual plan is. Is it this or is it this? So then we can just apply this argument again and again, and we'll get the machine status for every day, and will thus generate the entire schedule. So let me now conclude. So in this problem, in today's lecture, we saw another problem for which dynamic programming could be used. Okay. Before using the dynamic programming, there was an important step that we took, which is actually quite an important and interesting step. Very often we are given problems for which, to devise recursive algorithms, we need to generalize the problem formulation itself. So here was one such example. You must have seen a similar example in another problem, which was the problem of median finding. If we want to devise a recursive algorithm for median finding, well, we can't do that very easily or very simply. So what we do instead is we generalize the problem and ask for a recursive algorithm for finding the rth smallest. So some similar issue was applicable here as well. I would like to make a comment about dynamic programming, and that comment simply is that dynamic programming can be thought of as recursion. Okay, a basic idea, the first basic idea is recursion, and the next idea is make sure that you compute every value only once. And our table essentially made us focus on what values we were computing, and thereby we could make sure that we only calculated every value once. Finally, I would like to draw your attention to recursion itself and point out that when we use recursion in any search problems, it can be thought of as a divide and conquer of the search space. So with that, I will conclude this lecture.